Hey everybody, welcome back. It's Mr. G. Today we're going to be doing Power Electronics Lab number 10, DC Switching Regulator and Buck Converter. We have looked at this circuit before. We did a lecture on it. If you can't remember or haven't seen it, it is posted up on our YouTube channel. So you can go and do a review if you need, or if you've never seen it and would like to, by all means pay a visit. It's the same circuit that we had dealt with before, which is this one right here. We have our buck converter and the control. So the buck converter consists of the switching device, which is here, our inductor, our capacitor, our load, and our diode. The bottom part here is our circuit that controls the duty cycle at which we turn this on and off. So again, this is the control circuit, so that's down here, and its job is to control the switching device on and off. So, before we get started, there are some things that need to be set up. I've already taken the liberty to do so. Set the power supply for 20 volts, so we've got 20 volts coming in. So I'll show you here. 20 volts coming in. Place a jumper from A to B, which we've done. Place a jumper C to D, place a jumper from F to G, place a 22K resistor in the R8 position, and place a 56K resistor in the R11 position. Now, I'm going to adjust the value of VR4, which is this pot right here, until we get 10 volts out. So I've already got it adjusted, but what I'm going to do is I'm going to just play with it a little bit, show you that we can drop down the voltage or bring the voltage up, go above 10 if we want. But where we're going to start is at exactly 10 volts, which is right there. So we've got 10 volts. So that's the circuit. First thing we're going to do is observe and sketch the waveform at test point 1. Test point 1 is at the top of the diode, which is right there. So test point 1 is connected onto our scope. We're going to look at that waveform. We're going to look at the voltages and the data. So here is the waveform already on the screen for us. As far as the data goes, the period is 472 microseconds, so 473 microseconds. The frequency is 2.11 kilohertz. The voltage is approximately 23 volts, give or take, peak to peak. We've got a lot of noise at the top here, so it's probably why we're a little bit above the 20 volt level. But peak to peak, 22, 23 volts. What we also want to do is we want to look at the duty cycle. If you remember from the lecture, duty cycle is a measurement of the time that the pulse is high over the period. We already have the period, so the period is 473 microseconds. Now we're going to try and measure this time up here that this thing is high. So I'm going to put the cursor on, and I'm going to move my lines in right there. So from that line to that line is a measurement that the pulse is high, and we're looking at 248 microseconds. So 248 microseconds. So calculating our duty cycle, 248 microseconds divided by the period, which is 473 microseconds, times 100%. That is going to give us the duty cycle for this particular waveform. So what we're going to do now is we're going to adjust the pot and drop the output voltage down to 8 volts. So we're going to take the pot, I'm going to drop the output voltage down to 8 volts. There we go. So now we have 8 volts at the output. What we want to do is we want to measure the duty cycle. I left the cursor in place, and you'll notice that now the waveform is considerably smaller than what it was before. So to take a good measurement, we're going to go cursor. Again, that one's going to come onto that line. This one's going to come back over to there. And we're going to measure 200 microseconds. So the pulse is now 200 microseconds over the period, which hasn't changed, which is 473 microseconds. So the period itself, 473, and 200 microseconds is the time of the pulse. So we can use that and calculate our duty cycle at 8 volts. The next is we're going to increase the output voltage to 12 volts. So there we go. So we got the voltage up at 12 volts now. So our output voltage is 12. You'll notice I left that cursor line sitting there. You'll notice that the pulse has now widened out quite a bit. So we will now measure what the new time is. So again, that cursor staying on that line. Bring this one out to this line. So now we've increased to 288 microseconds, and the period still remains the same at 473 microseconds. So the pulse width has gotten bigger, so the time on has gotten bigger. So our duty cycle has increased. So an increase in duty cycle causes our output to actually get bigger. So now we're going to go back to our initial case so that we have 10 volts at the output. Volts back at the output. The next step, step number 7. In the lecture, I talked about something called line regulation. Line regulation is basically a measure of how good a regulator is at maintaining the output when the input voltage changes. So when the input voltage actually changes, how good is the regulator at keeping that output constant? So what we're going to do is I'm going to go back to the input voltage here. I am going to increase the input voltage to 25 volts. So now the input voltage is 25 volts. Let's see what kind of an effect that 5-volt change had on the output. So if we look, the output is changed by 0.4, 0.5 volts. So that means 5-volt increase on the input side has only translated to a 0.4 volt increase on the output side. So again, at 25 volts, the V out is 10.4, 10.5 volts. The next step is to drop V in to 15 volts and see what happens at the output. So I'm going to go back over here. I'm going to drop V in to 15 volts. And now I'm going to take and look at what the difference is on the output. So now I've dropped 5 volts in input, and it causes a drop of 0.7 volts on the output. So when I look at this, if I'm looking at this one here, a 5-volt increase caused a 0.5 volt change. A 5-volt decrease caused a 0.7 volt change. What's next is to calculate the percentage line regulation. On the front page of the lab, there's a formula for percentage line regulation. It's the change in the output over the change in the input times 100%. So we're looking at a 0.5 volt change over 5 volts, And the other case was a 0.7 volt change over 5 volts. Okay, so this is percentage line calculation. What we're going to do is going to go back to the initial case. We're going to set Vin back to 20 volts. So we're going to go back to our initial case, put Vin back to 20 volts. And we're going to go here and measure the frequency at test point 1. So the frequency at test point 1 we already looked at, 2.11 kilohertz. So it hasn't changed. What's going to ask us to do now is replace the 56K at R11 with a 39K and see how that affects our frequency. So I'm just going to turn off the power for a sec. I'm going to pull this out. I'm going to put the 39K in and see what effect this has on frequency. Turn the power back on. You'll notice now that the frequency is almost 3 kilohertz. So the frequency has changed. So when I put the 39K in there, the frequency is now 3 kilohertz. I will turn off the power again, and I will go back to the initial 56 kilo ohms. And turn back on. And now we're back at the 2.11K. So when I drop the value of resistance, the frequency went up. So we're back to our initial case right now. Everything is back, and we're moving on to step number 14. Step number 14, sketch the output waveform and show voltage ripple. So we're going to take our scope, move it to the output, and take a look at the waveform. So when we look at the waveform, it looks pretty steady. But what we actually have is a very small AC ripple on top of 10 volts of DC. So what I'm going to do is I'm just going to drop this down to there. And you can see that we actually have 10 volts of DC and the wavy line on top. So what I'm going to do to be more accurate, I'm going to show you what the ripple looks like. So what I'm going to do is I'm going to get rid of the DC component and drop it down right there like so. So the DC part's gone. So now I can actually take a look at my scale, and that is the ripple. So this voltage here, 100 millivolts per division, so there's 300 millivolts approximately. So 300 millivolts of ripple sitting on top of the DC voltage at this point. So when you draw this waveform, it's not going to be a straight line. You're going to have some ripple. How much ripple? You actually have about 300 millivolts of ripple. So I'll just drop this down to that line. So each one of these squares is worth 100 millivolts. So there's about 300 millivolts of ripple sitting on that waveform. Okay, so sitting at the output. Step 15 says add a 100 microfarad capacitor in parallel with the other one that's there. So what we're doing is we are increasing the storage capability, and therefore we are reducing the ripple. So now watch what happens to that 300 millivolt ripple when I connect this capacitor. So I'm going to take it off, run, stop. Okay, so all of a sudden now we have a very, very small ripple. I'll take the capacitor out, big ripple, put the capacitor back, small ripple. So now this ripple is, if the other one was 300 millivolts, This one is about 40-ish millivolts. So it's a considerable difference in the actual size of the ripple with the added capacitor. So basically on this waveform, again, riding on top of the 10 volts DC, you have this little ripple. This one is going to be a big ripple. This one's going to be very, very small. Step 16, remove the cap. Remove the cap. We are going to add another resistor, another 100 ohm resistor in parallel with the first one. So what we're doing is increasing the load. Remember from the discussion in the lecture video, when we make the truck work harder, because we are increasing the load. If we increase the load in the back of a truck, we're making it work harder. What we're doing to this power supply is making it provide more current. So we are loading it more. So what we're doing is we are basically reducing the resistance, because we put two in parallel now, reducing the resistance, which increases the load on the circuit. So now we're demanding more from the circuit because the resistance at the output has changed, and the resistance has actually gone down, requiring more current. So now what we want to do is we're going to measure V out and duty cycle now that we have done this. So our V out is now 9.9 volts. We're making the circuit work harder. How much harder? Basically, we're trying to draw twice the amount of current. But the regulator itself is still maintaining pretty close to our 10 volts. So 9.9 volts. This is all a measure of what's known as load regulation. So load regulation is basically we have a no load minus full load divided by full load times 100%. So the normal load or no load condition, that would be our one resistor value. Our full load is actually with the two resistors in parallel. So we're looking at the full load condition right now. It asks us to measure the duty cycle. So I'm going to take my off run stop, go back and get our waveform nicely on the screen. There we go. Again, let's put it back into DC so we get a good look at our waveform. So now it says measure the duty cycle. Our frequency has not changed, so therefore our period is still 473 microseconds. Our value of our time high is 248 microseconds. So the duty cycle is going to be 248 microseconds divided by our period, which was 473 microseconds. Okay, so I'm going to show you something. Watch what happens to the duty cycle when I pull this resistor out again. Okay, the duty cycle actually drops. So what happens in order to keep our output high is the system itself automatically adjusts. It detects that the value of voltage is going down because of the extra load, so it access to or automatically adjusts so that the duty cycle increases ever so slightly to maintain our 10 volts at the output. Okay, so basically what happens is as the load tries to cause the voltage to go down, the circuit compensates by bumping up the duty cycle a little bit to increase the output voltage to maintain our 10 volts. So voltage out, 9.9, 10 volts, duty cycle. Duty cycle should be a little bit higher than our original case. So the no load or normal load is when there was one single resistor, which was 100 ohms. The full load condition is when we had two resistors in parallel, giving us 50 ohms. You can use the formula at the beginning and calculate the percentage load regulation. So that is number 17. 18 says remove the load. We're going to turn off the supply for this next step. We're going to remove the jumper from A to B, and replace it with a 10 ohm resistor. And what we're going to try and do is we're going to try and get an idea of what the current looks like by looking at the voltage flowing through the output. So this resistor is now in line with the output. So the current is flowing through that resistor, getting to the output. Before we had a short circuit. Now we're actually putting a resistor there. And what we're going to try and do is we're going to try and measure the value of current, or look at the value of current for that particular resistor. So now the way we're going to do this is we are going to put the oscilloscope, one channel of the scope is going to be on the one side of the resistor. Then we're going to put another channel on the secondary, or on the other side of that resistor. We're going to put both scope waveforms on the screen, and we're going to use something called the math menu to look at what the waveform, if I was to subtract that waveform from that waveform, what it actually looks like. So again, channel 1 of the scope is going to be on this side of the resistor. Channel 2 is going to be on this side of the resistor. What I want to do is I'm going to put both on the screen so that we are looking at two waveforms. There's one waveform. There's the second waveform. Okay. So if you look at the waveforms, if I put them right there on top of each other, they're pretty darn close. Okay, so let's see here. Where are we? There we go. So there's our other waveform. So I'm going to put their grounds together right there and drop this one right on top. And you'll look, there is an actual difference between these two values. So the difference between these two lines is actually the voltage drop across that resistor. So if we can figure out what this voltage drop is, we can use Ohm's law and figure out what the current actually is at the time. So what we've done is we have basically got a waveform which represents this side, a waveform which represents this side. Now what we're going to do is we're going to introduce something called the math menu, and I'm going to take one value and minus the second value. So this third line that has come up, and I'll drop this down. So let me see, where is my, if I'll be able to do that with this scope. So there is the grounding point. This little waveform here is actually the value of the difference between this one and this one. Okay, so we've got difference between 1 and 2 is actually shown here. So what I'm going to try and do is I'm going to try and make this so we can see the waveform a little better. Okay, so again, this is the waveform on one side, this is the waveform on the other side of the resistor. If I took those two waveforms, so go get rid of the math menu, I took those two waveforms, let's freeze it, there we go. Took those two waveforms and wanted to find out what the difference is between those two. That is this waveform. So this one, grounds are down here, large waveform. Okay, remember this is riding on 10 volts. This is just the waveform that represents the difference between those two. Okay, so if that's the case, what I'm going to try and do is I'm going to try and measure the peak value here with respect to the ground, which should be there. So 1.36 volts. So what we're looking at is on this particular waveform, the top of the waveform is 1.36 volts. The bottom, or the minimum of that waveform, whoops, wrong cursor. The minimum of that waveform is about there, which is 720 millivolts. So 720 millivolts is the minimum. The maximum was 1.3, 1.35, 1.36 volts. The average would be the difference between the two. So now what you're going to do is you're going to take the 1.36 volts and you're going to divide it by the 10 ohms. And then you're going to take the minimum value, whatever we had come up with, 720 milli, whatever that was, and you're going to take that value and divide it by the 10. And then you'll take the average between the two and divide by 10. And what you end up with is maximum current, minimum current, and average current. So you're just using Ohm's law. We're measuring a voltage. That voltage, that waveform, is actually the voltage drop across that resistor. So that's giving us maximum voltage across, minimum voltage, so the difference between the two. So we get a max current, a min current, and then divide by 2, and you end up with an average. So we can split right down the middle what would be the average current flowing through. Okay. So what we're going to do is turn the power supply off again, so I can remove this resistor, and that's all right. And we're going to put that jumper back in there. And we just have one more step to do. What we're going to do is we are going to measure the DC input current coming from the supply so you can calculate the load current going out. Okay, so the input current and load current. Okay, so that would be the current coming out here through our load. We know it's 10 volts, and we know that you have a certain resistor value here. That's going to be the DC current, and then you can figure out what the efficiency is. So what we need is the current coming in from the supply. So what I'm going to do is I am going to quickly take this out of here, put it into here. So I've turned my voltmeter into an amp meter. So current is going to come out, it's going to go into the meter, it's going to then return to my circuit like so. I need to pick milliamps here, we're DC, and I'll see if I can find a decent value for it. So let's turn this power back on. So we're looking at 66 milliamps. So 66 milliamps of current is my current flowing out of the power supply. Okay, so flowing out of the power supply, 66 milliamps. The current that you're going to get at I out is the voltage, which is 10 volts, divided by your resistance, which is 100 ohms. Okay, and then you're going to calculate the efficiency, which is here. The rest, there are some questions for you to answer. 1, 2, 3, 4, and 5 questions as part of the lab. So, those are all the measurements that are required for you to complete the Power Electronics Lab number 10, DC Switching Regulator and Buck Converter. So I hope this was helpful. So everybody take care, have a great day, and see you again next time.